In this video, we'll begin our discussion of what's called circulation in a vector field given a path. So this relates very much so to work. The explanation is exactly the same. So the circulation of F along C is a measure of how much the vector points in the direction of C. So that's that same thing with that work idea, that I have some tangent vector, and we're still going to use tangent vector on C because it tells me where we're going, and then I'd have some other function, right, the force field pushing on that point there, or we can move it up, either way, and I want to know, let's move that up. Come on, okay. That is my F. Sorry that it got caught up with that. This is my T. And all the circulation is a measure of how much of the vector field points in the direction of C. It sounds like work because it's the same measurement. We want to know what is the component here that's being forced down onto T, right? We want to know how much of F is pushing that way. We could actually list out, and we'll see a picture in a moment, the difference between our tangent vectors and then what the force field actually does. So the force field will push it and help it that much. More simply, another way to think about this, and I wrote it here, is how much of the vector field is at your back and how much of it is in your face. To determine calculation, we simply add up the components of F in the direction of the unit tangent vector T. Again, remember, back to that motivation assignment, if I want something that's in the direction, I want to know how much they contribute to each other, I just take my dot product. Again, this definition, I wrote it out here. This definition becomes F dot T ds, but using the calculations that we came up with earlier, this is T equals A to B of F dotted with R prime of T dt. That's what we're mainly looking for. Okay, we want to look at the circulation. Remember, circulation is how much of the vector field is going with C. We're going to look at two different things. We have a radial field that distributes out the whole time, and we have a rotational field. So we have both. Okay, they want us to find, we have the unit circle counterclockwise on the picture there, find the circulation on C. So let's go ahead and define R. Okay, R of T, it's just a unit circle, radius of 1, so it's going to be cosine because that's X, and then sine, that is Y. And then we still have the same T's, 0 to 2 pi for the whole circle. And then in our definition, we need R prime. So I'm going to go ahead and find R prime here. R prime is negative sine T, cosine T. And then they want us to try to find the work, or circulation, right? Same calculation. Circulation of C, given that C lives in the radial vector field x equals y. So that spits it out. You can see the vectors, just a few of the representations of the vector spitting it out that way. So if I want to find the circulation is equal to C F prime. Let's go ahead and just change those. We already know from above it's going to change. F prime to R prime T dt. So all I got to do is plug that stuff in. I do need to put F in terms of T. So F of cosine T sine T, that's going to be equal to cosine T sine T. That is the vector. It's just a straight replacement. So we're multiplying, dot producting this and that. Let's go ahead and just do that before I throw it in the integral. I think that's a little easier than seeing it there. So we can even move A up because this is still part of A. F dotted with R prime is equal to negative sine cosine. Don't forget your arguments. Sine T cosine T. And then plus sine T cosine T. And that gets me a 0. So the integral runs from T equals 0 to T equals 2 pi of 0 dt, and that equals 0. So this makes sense though. Think about your radial vector field. We know that all of these meet at a 90-degree angle just by the definition because the slope is y over x. So they meet at that point. So every time if they meet at a 90-degree angle, each time the vector field actually isn't helping C at all. The circulation is 0. It's not hurting C. It's not at the force, the wind, the water, whatever we're talking about in our vector field is not at our face, not pushing against our face or pushing on our back. It's pushing out, keeping me, I mean, I guess you could say it could push off a C for sure, but it doesn't help. It doesn't go in the direction of our tangent vector or C. Right, we're going to do B. B is the same setup, except for, okay, let's write down R prime of T is the same, so I don't have to calculate that, I can just copy it. Guess I could have copied and pasted. And then F, we got to put it in terms of this new function, which is going to be negative, or we're going to plug in X and Y, so it's still cosine T, sine T. This is we plugged in RT, and then we're going to get negative sine T, and then X cosine T. That's my vector. There we go. Let's dot those two. All right, dotting them. I got negative sine squared T plus, it's going to be positive actually because a negative times a negative, and then cosine squared T. You can see where this is going to end up. That's a 1. So to find the circulation is the integral from t equals 0 to 2 pi, that was from way above, of 1 dt, which is just 2 pi. Well, this makes sense. That's going to be, I think, our maximum, because if it is a rotational vector field, if we look up there, our vector field, that points in the direction that probably our tangent vector would point in. It does, actually. It's a direct application of it. So it actually helps it out quite a bit. The whole time, the C is getting pushed along, right? It's at our back. It's not headwind, it's pushing, tailwind pushing us forward through C, or water, or whatever the vector field represents. It's pretty neat stuff. So remember, circulation is similar to work. It makes sense, too. Circulation tells you what's pushing you and holding you back. Work from the vector field will tell us that as well in a different manner.